At 0412 hours local time, the rail bridge spanning the North Crimean Canal ceased to exist as a functioning structure. The first span came down in 4 seconds. A shaped charge warhead punched through the eastern bearing column, the focused metal jet severed the load-bearing steel at the connection point, and 47 tons of bridge deck dropped 11 meters onto the canal bank below. The second span followed 9 seconds later, when the western column, already weakened by the blast wave, failed under the redistribution of load it was never designed to carry alone. The impact threw canal water 60 feet into the air. On the thermal feed overhead, the bridge signature, a clean, rectangular heat source from decades of rail traffic, disappeared and was replaced by 2 ragged thermal blooms where the collapsed steel met the wet earth. Rewind 8 minutes and 30 seconds. The first drone to reach the bridge structure hit the northern approach embankment, the earthwork ramp leading onto the bridge deck from the Kherson side. The explosion gouged a 2-meter crater in the compacted soil. No structural damage to the bridge itself, no secondary. The bridge remained intact. The freight train sitting 3 kilometers north on the approach track, loaded with 340 tons of artillery shells and fuel, had not yet begun to move. The operation had nearly ended there. 14 drones had launched. 6 were already gone, shot down, or jammed into the ground over the Kherson steppe. 1 had just wasted its warhead on dirt. 7 remained. The bridge was still standing. This is how they finished it, and why this particular crossing mattered more than any other span in Crimea. To understand what happened here, you have to go back 4 days. The North Crimean Canal Bridge is not a famous structure. It does not appear on tourist maps. It carries no name that Russian state media broadcasts. It is a single-span railway crossing 94 meters of reinforced concrete and structural steel built in the Soviet era to carry freight trains from the Ukrainian mainland into Crimea across the canal that feeds water to the northern half of the peninsula. There are longer bridges in the region. There are more photographed ones. But this crossing is, by a significant margin, the most important rail link Russia still controls into northern Crimea. The Kerch Bridge carries traffic from the east, the North Crimean Canal Bridge carries traffic from the north, and the northern route is shorter, faster, and capable of running heavier freight loads per day than the Kerch corridor. Every artillery shell, every fuel tanker, every armored vehicle replacement that Russia moves from its Zaporizhzhia staging areas into Crimea comes across this bridge or goes the long way around through Kerch. Destroy it, and you do not slow Crimea's supply chain. You cut one of its 2 arteries. Ukrainian military intelligence had been tracking the crossing for 11 weeks. Not because it was an easy target, it was not. It sat inside a layered defensive perimeter that had been deliberately constructed after the Kerch Bridge strikes demonstrated how vulnerable fixed infrastructure was to aerial attack. Russia had ringed the canal crossing with overlapping radar coverage, positioned mobile short-range air defense assets within direct visual range of the bridge deck, and run Krasuka-4 electronic warfare vehicles along the approach roads on rotating schedules so the jamming footprint was never predictable. Russia believed the bridge was protected. Russia believed the combination of radar, missile coverage, and electronic warfare made a drone strike on this specific structure effectively impossible. The approach corridors were too exposed, the defensive density too high, and the flight time from Ukrainian territory long enough that any strike package would be tracked and engaged before it reached the canal. But what the Russians did not know was that Ukrainian intelligence had spent those 11 weeks mapping not just the bridge, but the gaps, the radar rotation cycles, the times each morning when the Krasuka-4 vehicle repositioned, leaving a 15 to 20-minute window in which its jamming footprint shifted south and left the northern approach corridor temporarily uncovered. The position of the Tor M2 launcher that covered the bridge from the east, and the fact that its crew rotated at 0350 hours each morning, creating a 4-minute window during the handover when the system's radar was in standby mode while the new crew ran their startup sequence. The operation was authorized at 1800 hours, 3 days before the strike. The force package launched from 2 separate positions inside Ukrainian-controlled territory at 2347 hours. The force package consisted of 14 aircraft divided into 3 distinct elements. The recon element was a single Leleka 100 fixed-wing WAV, Ukraine's domestically produced long-endurance reconnaissance platform. With a flight time exceeding 3 hours, optical and thermal imaging payload, and an encrypted data link that allowed real-time video transmission to the operations center while the aircraft loitered at altitude above the engagement area. It had been in position over the canal zone for 90 minutes before the first strike drone reached the outer defensive perimeter. Its job was not to guide individual drones, it was to watch the entire defensive network and call the timing window. The primary strike element was 9 UJ-26 Beaver fixed-wing drones. The UJ-26 is Ukraine's most capable purpose-built strike platform in this weight class, a 75-kilogram aircraft with a 500-kilometer operational range, a cruise speed of 120 kilometers per hour, and a payload capacity of 20 kilograms. The warheads fitted to this package were shaped charge heat rounds modified with delayed fusing. The drone would strike the bridge structure at a shallow angle. The shaped charge would initiate, and the penetrator would drive through the concrete cover before the main detonation transferred energy into the steel rebar beneath. Against a bridge-bearing column, a structure that fails when its steel skeleton is severed. Not when its concrete shell is cracked. This fusing sequence was the difference between making a dent and bringing the span down. The third element was 4 FP2 quadrotor drones carrying 2 warhead configurations. 2 carried standard heat charges. 2 carried electronic spoofing payloads, modified sensor packages designed to mimic the radar return of a much larger, faster aircraft. Their job was not to strike the bridge. Their job was to be seen, to be tracked, and to pull the Tor M2 launcher's fire control computer away from the approach axis the UJ-26 formation was using. The stakes were established in the planning brief and they did not change. The UJ-26 airframes cost between $85,000 and $120,000 each. The bridge structure, if repaired assuming Russia could source the materials and move the repair crews, would require a minimum of 6 weeks of work and an estimated cost of several $1 million. The freight it was blocking? A single fully loaded military supply train represented between 340 and 500 tons of material. At truck equivalent rates across the Azov corridor, replacing one train's cargo capacity required 140 to 200 truck movements through roads that Ukrainian long-range fires were already targeting. The bridge was not a bridge. It was a math problem, and Ukraine had solved it. The outer radar layer covering the canal bridge was a 1L-122 Garmon battlefield radar, a compact, vehicle-mounted system designed specifically for detecting small, low-flying targets, including mortar rounds, artillery projectiles, and unmanned aircraft. The Garmon operates in the X-band and can detect a target the size of a crow at 12 kilometers. It was positioned on an elevated ridgeline, 8.4 kilometers north-northeast of the bridge, giving it overlapping coverage of both the northern and eastern approach corridors. Against a conventional attack profile, drones flying straight in at low altitude on a predictable heading, the Garmon would have been decisive. It would have handed tracks to the Tor M2 battery with 8 to 10 minutes of engagement time available. At the Tor M2's engagement rate, that was more than enough time to service every drone in the package. The UJ-26 formation's answer to the Garmon was neither speed nor stealth. It was geometry. The 9 strike drones approached not from the north, the direct route from Ukrainian territory, but from the northwest, routing along the Dnieper floodplain at an altitude of 11 meters above the waterline. At 11 meters, the Dnieper itself provided terrain masking. The riverbanks, the reed beds, the low scrub of the flood delta rose between the Garmon's radar beam and the drones threading the river corridor below. The Garmon's effective detection range against targets below its radar horizon dropped from 12 kilometers to effectively 0 for anything flying the river line. The 4 FP2 spoofing drones did not use the river. They climbed to 200 meters due north of the bridge and activated their radar signature amplifiers. On the Garmon screen, they appeared as 4 aircraft roughly the size of Su-25 ground attack jets, large, fast, approaching at altitude. The Garmon operator flagged them immediately. The track went to the Tor M2 fire control computer. 2 of the 9 UJ-26 drones were shot down in the river corridor anyway, not by missile, but by Strela-10 short-range infrared guided missiles fired from a concealed position on the western bank that the Leleka 100 had not fully characterized. The missiles guided on the engine heat of the UJ-26 power plants. Both aircraft went in within 40 seconds of each other. 7 remained. They continued south along the river, below the Garmon's coverage, toward the canal. The Tor M2 battery, covering the bridge from the east, was, on paper, the most dangerous system in the defensive perimeter. The Tor M2 is a short to medium-range air defense system purpose-built for exactly this threat environment: small, fast, low-altitude targets that larger systems cannot engage. Its 9M338K missiles are effective against targets flying as low as 10 meters above ground level, with a minimum engagement range of 1 kilometer and a maximum of 16. The system carries 16 ready missiles per launcher. Its 9S-932 fire control radar can simultaneously track up to 48 targets and engage 4 of them at once. In a symmetric engagement one-threat axis, predictable approach profile, the TOR-M2 is close to an ideal point defense system for a fixed infrastructure target like a bridge. The TOR-M2 crew rotated at 0350 hours. The new crew required 4 minutes and 20 seconds to bring the system from cold standby to full operational status. The Leleka 100 had observed this handover sequence on 3 consecutive mornings. The timing was consistent to within 30 seconds each cycle. The UJ-26 formation reached the canal's northern bank at 0352 hours and 40 seconds. The TOR-M2 was still in its startup sequence. The radar had not yet locked, but what the defensive planners had not anticipated was the configuration of the approach. The 7 surviving UJ-26 drones were not flying as a formation. They were split across 3 approach axes, 2 from the northwest along the river exit, 3 from the west crossing the open farmland behind the Krasuka 4's current position, and 2 more coming from almost due south, routing back up the canal itself from the direction the defenders had never considered a viable attack vector because it put the drones over Russian-controlled territory for the last 6 kilometers of the flight. The TOR-M2 came online at 0354 hours and 12 seconds. Its radar swept and found not 7 small targets on one axis. It found targets on 3 axes simultaneously. The fire control computer began sorting. It locked the 2 drones on the southern axis first, because they were closest to the bridge deck and their approach geometry gave the system the shortest engagement window. It launched 2 9M338K missiles, both connected. The drones on the southern axis were destroyed at 0355 hours, 800 meters short of the bridge structure. 5 UJ-26 drones remained. The TOR-M2 was reloading its engagement queue. The Krasuka 4 electronic warfare vehicle activated at 0354 hours and 31 seconds almost simultaneously with the TOR-M2 going hot. The Krasuka 4 is one of Russia's most capable ground-based U systems. It operates across a wide frequency range and is specifically designed to suppress airborne radar, satellite communications, and drone navigation signals. In this configuration, positioned on the approach road 3.1 kilometers west of the bridge, it was broadcasting in the L-band and S-band frequencies used by most Ukrainian drone navigation systems, while simultaneously spoofing GPS signals across a 300-kilometer radius footprint centered on the canal crossing. For the 3 UJ-26 drones approaching from the west, the effect was immediate. Their GPS receivers receiving the Krasuka 4's false satellite signals at substantially higher power than the actual GPS constellation began showing position errors. One drone turned 17 degrees north, following a false coordinate set that would have taken it into the open steppe. Another descended 20 meters below its planned flight altitude, responding to a false terrain avoidance calculation. For 48 seconds, 2 of the 3 Western approach drones flew on degraded navigation. Then, the inertial measurement units flagged the anomaly. Each UJ-26 in this package had been fitted with a dual redundancy navigation system, a GPS receiver running alongside a strapped-down inertial navigation unit that tracked the aircraft's position using accelerometers and gyroscopes independent of any external signal. When the GPS position solution diverged from the in solution by more than 150 meters, the flight computer locked out the GPS receiver and transferred navigation authority to the in system, supplemented by optical flow navigation, which used the aircraft's downward-facing camera to track ground features against a preloaded terrain map. The terrain map for this mission had been built from 6 weeks of Leleka 100 observation. The canal itself was on it. The irrigation drainage channels running west from the canal were on it. The elevated road embankment 3 kilometers south was on it. As the drones switched to optical flow navigation, their position uncertainty, which had briefly expanded to 300 meters under the Krasuka 4's spoofing, collapsed back to within 40 meters. They reacquired their approach vectors. The Krasuka 4 had bought Russia 73 seconds. It had not bought the bridge. The irony was structural. The Krasuka 4 vehicle had been positioned specifically to protect the bridge from drone attack, and its jamming footprints centered on the crossing had acted as a navigational reference point for the drones that had already switched off their GPS. The optical flow systems used the canal, the road embankment, and the drainage channels to navigate. All of those features ran toward the bridge. Russia's strongest electronic countermeasure had pointed its own threats at the target it was trying to protect. At 0356 hours and 41 seconds, the first of the 5 surviving UJ-26 drones reached the bridge structure and struck the northern approach embankment. The warhead detonated. The explosion was clean, contained, and structurally irrelevant. The shaped charge had been designed to engage a steel-reinforced bearing column, not compacted earthwork. Against the approach embankment, soil and rock with no steel skeleton to sever the detonation produced a 2-meter crater and a pressure wave that cracked the concrete edge of the bridge deck at the abutment. No span movement, no bearing failure. The bridge held. On the Lelica 100's thermal feed, the bridge signature did not change. 4 drones remained. 3 had target solutions on the bearing columns. One was holding in a racetrack orbit 1.4 kilometers north, waiting. The Tor-M2 had resorted its engagement queue and was now tracking all 4 remaining aircraft. It launched 2 more 9M338K missiles at 0357 hours and 8 seconds, targeting the 2 UJ-26 drones on the northwestern axis, which were the closest to the bridge and carrying the warheads designated for the eastern bearing column. The first missile connected. The second did not. The targeted drone executed a pre-programmed terminal evasion maneuver, a descending left turn that put the drone behind the bridge abutment wall for the final 600 meters of its approach, using the concrete structure itself as cover from the Tor-M2's radar. The missile, losing lock as the radar return disappeared behind the abutment, continued on ballistic trajectory and detonated against the embankment bank 80 meters east of the bridge. 3 drones remained. The Tor-M2 was reloading at 0358 hours and 52 seconds. The first successful structural strike hit the eastern bearing column. The UJ-26 flew its terminal approach at 14 meters above the canal surface, using the water as radar masking for the final 400 meters. It struck the eastern bearing column at the base of the deck connection point, the most structurally critical location on the span, where the vertical load of 47 tons of bridge deck transferred into the column. The shaped charge initiated on contact. The penetrator drove 340 millimeters into the reinforced concrete shell before the main charge detonated. Inside the concrete, the detonation produced a pressure front moving at 8,500 meters per second. The concrete cover spalled inward. The main charge found the steel rebar matrix, 8 32-millimeter bars running vertically through the column, and the focused energy of the shaped charge jet severed 4 of them cleanly. The remaining 4 bars, carrying a load they were not designed to handle alone, began to elongate under the stress. The column did not fail immediately. It began to fail. The deck above the eastern column shifted 23 centimeters laterally in the first 3 seconds after the strike. Then it stopped. The bridge was damaged. It was not yet down. The freight train 3 kilometers north, which had received orders to begin moving south 30 minutes earlier, was now 1.8 kilometers from the northern approach. Its driver could see the smoke from the embankment strike. He applied the brakes. At 0400 hours and 17 seconds, the second structural strike hit the western bearing column. The approach had been the most difficult of the operation. This UJ-26 had been the drone flying the southern axis along the canal itself. The 2 aircraft on that axis that the Tor-M2 had targeted first. Its wingman had been destroyed. It had continued south alone, below the Tor-M2's radar coverage for the last 2 kilometers because the canal bank rose above the system's minimum engagement elevation at that range. It struck the western column from the south, an approach vector that put it directly in line with the Tor-M2's radar dead zone created by the bridge structure itself. The western column received the same treatment as the eastern: shaped charge penetration, rebar severance, immediate load redistribution. But the western column was already carrying excess load. The eastern column's partial failure had transferred stress westward across the deck. When the western column's rebar was severed, there was no redundancy left. The eastern column failed completely at 0400 hours and 26 seconds. The first span dropped. The western column followed 9 seconds later. The canal bank absorbed 47 tons of bridge deck on each side. The impact sent water 60 feet into the air above the canal. The freight train, now stopped 1.4 kilometers north of the collapsed structure, was going nowhere. The bridge was gone. What the collapse of the North Crimean Canal rail bridge means cannot be measured only in concrete and steel. Russia's military logistics in Crimea operate on a narrow margin. The peninsula has no indigenous heavy industry, no significant fuel production, and no capacity to manufacture the artillery shells and missile components its forces require. Everything arrives from the mainland by road through the Azov corridor, by rail through Kerch, or by rail through the northern crossing that no longer exists. The Kerch Bridge, already damaged by previous Ukrainian strikes and operating at reduced capacity under constant threat, is not an adequate substitute for both crossings simultaneously. It was designed to supplement the northern rail line, not to replace it. The freight train stopped 1.4 kilometers north of the collapsed span was carrying, by Russian military logistics standards, a significant resupply package, 340 tons of material that intelligence assessment indicated was primarily artillery ammunition and diesel fuel for forward armored units in the Kherson axis. That train could not go around. There is no road bridge at this location capable of handling a loaded military freight consist. The train would have to be unloaded by truck. The cargo transported 140 kilometers east to the Kerch crossing, reloaded, and moved into Crimea by the alternative route, a process that would take days and consume fuel and vehicle capacity that Russia did not have in surplus. And this was one train. Behind it, on the northern Kherson rail corridor, more trains were scheduled. The deeper consequence is the pressure it places on Russia's decision cycle. Every time a critical piece of infrastructure goes down, Russia faces the same impossible arithmetic: repair it under threat of restrike, divert resources to defend it more heavily and accept the exposure elsewhere, or reroute supply through corridors that are longer, slower, and themselves under attack. There is no option that does not cost Russia something it cannot easily replace. The Kerch Bridge carries more traffic now because the northern route is periodically disrupted. More traffic on the Kerch Bridge means more exposure to strike. More air defense assets protecting Kerch means fewer assets protecting the northern approach. Fewer assets on the northern approach means a crossing like this one is more vulnerable, not less. Ukraine is not trying to destroy one bridge, it is trying to make every bridge in Crimea simultaneously too expensive to defend and too important to leave undefended. This operation was one more turn of that mechanism. The cost comparison that will never appear in Russian state media: the 14 drones in this package cost a combined total of approximately $900,000, including the 6 that were shot down. The bridge, its repair, assuming Russia can source the structural steel and move the construction equipment under continued threat, will cost several times that figure and require a minimum of 6 weeks to restore to operational capacity. In those 6 weeks, every supply that would have crossed this bridge will go the long way. Every truck that fills the gap will burn fuel. Every day the bridge stays down is a day the forces on the Kherson axis run one supply cycle shorter. $900,000 against 6 weeks of a peninsula's supply chain. The equation runs the same direction it always does. And here's the dimension that separates this strike from a demolition job: the bridge was not hit because it was the nearest target or the easiest one. It was hit because Russian forces in the Kherson axis had been increasing their artillery consumption rate over the preceding 3 weeks, a signature that Ukrainian signals intelligence had detected in the logistics traffic patterns on this rail line. Something was being prepared. The supply rate was climbing. And the fastest way to interrupt whatever was being prepared was not to target the forces themselves, it was to cut the line feeding them. The bridge came down. The supply rate on the Kherson axis dropped. Whatever was being prepared had to wait. Russia will repair this bridge. It has the engineering capacity and the strategic need to do so. When it does, Ukraine will have a decision to make about whether to let it operate or to strike it again. But that decision belongs to a future moment. The decision that mattered was made 4 days before the strike, in the planning brief where someone identified the crew rotation at 0350 hours and the 15-minute jamming gap in the Krasuka 4's repositioning cycle. That decision to wait, to watch, to map the gaps rather than the target is what made everything else possible. Ukraine did not destroy this bridge because its drones were powerful enough to break through Russia's defenses. It destroyed this bridge because its intelligence was patient enough to find the hour when Russia's defenses were thinnest. Patience, in this war, has proven to be the most dangerous weapon Ukraine possesses. What do you think Russia does next? Repairs the bridge and accepts the risk of restrike? Or reroutes everything through Kerch and accepts the permanent bottleneck? And what should Ukraine hit while that decision is being made? Drop your answer in the comments. If this breakdown gave you something the headlines didn't, hit like, subscribe to the channel, and turn on notifications so you don't miss the next one. We go deeper into the hardware, the tactics, and the decisions that everyone else is skipping over. Leave your thoughts in the comments. Goodbye.